In this video, we're going to talk about kinetic molecular theory. What we're going to do is we're going to use some basic laws of physics and some simple assumptions, and we're going to derive the gas laws that other people determined by experimentation. And so this is part of showing that the gas laws that we determined from experiment agree with the laws of physics. One of those basic things that we need to do as part of the scientific method, right? That our laws that we determine empirically agree with our theoretical laws of nature. So what are the assumptions that we have to make as part of this kinetic molecular theory approach? Okay, so one, we're talking about individual gas molecules. They travel in straight lines unless they collide with the walls of the container or with another gas molecule, right? That is that they act as Newtonian masses, right, with inertia, right? They travel in a straight line unless something acts on them, and momentum. Okay? So they act as masses traveling in a straight line, right, unless something acts on them. So the second assumption is one that we talked about when we talked about ideal gas. That is that the volume of the individual particles can assume to be zero, that the volume is negligible, right? And that the particles don't attract each other or repel each other, right? There are no forces exerted, right? So these are our ideal gas assumptions, right? That this gas that we're using as a model follows those things that we decided were appropriate for ideal gases. Okay? Now, another assumption is that the source of pressure in the container is the collision of the particles of the gas, the molecules, with the walls of the container, right? So it is collision of the gas with the walls of the container that is the source of what we measure as pressure. The other thing that we assume is that the average kinetic energy of the molecules of a gas is proportional to the absolute temperature. This comes from the Boltzmann-Maxwell relationships. One of the important Boltzmann-Maxwell relationships is that the average speed of molecules squared is equal to 3 times Boltzmann's constant times the temperature divided by the mass of the molecule. Well, if we multiply through by mass, we get mass times its speed squared equals 3K times the temperature. Well, we've got mass, if mass is in kilograms and speed is in meters per second, that's units of energy, right? Kinetic energy is 1/2 mass times velocity squared, right? So that is really equal to 2 times the kinetic energy for the molecule. And so that makes kinetic energy proportional to temperature in Kelvin. Right? So here is a visualization of that, right? So the Boltzmann-Maxwell relationships talk about the kinetic energy. They also talk about the speed as a function of temperature, right? So here we have the distribution of speeds, right? The number of molecules with each speed, right? So our peak is at this speed, but because we have an absolute limit at 0, right? No molecules are not moving. And we have a tail, right? We can have a long tail. The actual average speed is a little beyond the peak speed, okay? So that represents the average speed. Now, what we do is remember molecules are moving in all directions. And so the average speed of the molecules of a container of gas is 0, because for every molecule that's moving this direction, there's a corresponding molecule moving that direction. And so they cancel each other, right? So we have speed x and we have speed minus x. But if we square those, right, x squared equals x squared. Minus x squared equals x squared, right? Minus x all squared equals x squared. And so if we take the positive square root of x squared, we get x. And so that's how we get this idea of a root mean average speed. We take the average speed of the molecules in all directions, positive and negative. We square them, it makes everything positive. And then when we take the square root, we get a positive average speed. So here we're looking at the same distributions, the speed of the molecules versus the number of molecules that have that speed, right? But we're doing it at different temperatures. So look what we have here at 100 Kelvin, the average speed is lower, right? We get this kind of distribution, right? Now it's the same molecules, so at 200 Kelvin, right? The area under this curve is the same, but the curve is both wider and the peak has moved to the right and the root mean speed has moved to the right, right? So as the temperature goes up, we get a wider distribution of speeds, right? At 500 Kelvin, remember, this has the same area under it as the previous curve. And as we get 1000 Kelvin, it spreads out even more. Right? And it would come down and it would approach the limit out there someplace. Okay? So we can see right, from that equation we put up before, that the average speed squared equals 3 times Boltzmann's constant times the temperature divided by the mass of each molecule. If we multiply that times Avogadro's number, Boltzmann's constant times Avogadro's number is R. The mass of each molecule times Avogadro's number is the molar mass in kilograms. And so we get this relationship that the average speed can be calculated to be 3 times the gas constant R times the absolute temperature divided by the molar mass. Right? As long as the molar mass is expressed in kilograms per mole, right? And the R unit is in the joules per mole Kelvin unit. That is the 8.314 joules per mole Kelvin. Right? So we can calculate the average speed of the molecules in a sample of gas. So now, before we do our derivation, we have a couple of other things that we can assume. Right? So we're going to be working with here, right, n moles of gas. Let me make my pen a little bigger. Right? So some number of moles of gas. We're going to be working in a cubic container whose each side has a length L. So the volume is equal to L cubed, right? If we've got our cubic container, right? This side is L, this side is L, and the depth is L, right? So length times width times height gives us L cubed, right? We've done this before. Mass represents the mass of an individual particle, but expressed in kilograms, right? Oh, and our lengths are expressed in meters. And collisions are elastic. This is related to assumption number 3, that there is no attraction between particles. And so what that means is that the kinetic energy of the particles pre-collision is equal to the kinetic energy of the particles post-collision, or the mass times velocity, which is the momentum, right? The momentum pre equals the momentum post-collision. Okay, this was a little difficult to represent, but I tried, right, as a way of explaining how we get the average speed. So say we have a particle moving in the box, and it's not moving, right? So here is our box of length L on each side. So this is L, and the depth is L. And we have a particle not moving in either the X, the Y, or the Z direction, right? It's moving at angles to all three, right? So if we can create a vector for its velocity, u, we can divide that into vectors, right? So here it's going from the front right corner of this rectangular box to the back or upper left corner of the the back upper left corner of the rectangular box. And so we can divide that velocity into 3. There's a velocity in the x direction. It's going from here to here in the x direction. There's a velocity in the y direction. It's going from here up to the top of the box. So that would be here to here x, here up to here y. And it's also going front of the box to the back of the box in the z direction. And so those would all add up to, right, moving here, that's the x, moving here, that's the y, moving here, that's the z, right? And so we can divide our motion diagonally across the box into 3 separate movements that go along the sides of the box. And so then we can express the original velocity, right? Because it is a hypotenuse crossing from lower right front to upper left rear, right? Lower right front to upper left rear. If we, it is a hypotenuse, so that hypotenuse of that box is equal to the movement in the x direction squared plus the movement in the y direction squared plus the movement in the z direction squared. And so we can express the overall velocity vector in terms of the 3 vectors, component vectors, one in the x direction, one in the y direction, one in the z direction. Now, let's just consider one component of that, right? So if we take our box and only consider motion in the x direction. So we're talking about, right, we're looking at this square on this side and this square on this side, right? And so we're only at first going to talk about collisions with the particle on this side of the box and on this side of the box. That is, those caused by movements in the x direction. And so we can express the collision frequency. How often does our particle hit this side of the box or this side of the box? Right? That frequency of collisions in the x direction is equal to the speed at which the particle is moving in the x direction divided by the length, right? Speed divided by length. Speed is in meters per second. Length is in meters. Meters per second divided by meters gives us 1/seconds. So this tells us how many collisions we have with the wall per second, right? So collisions with the wall per second can be expressed that way. Speed in that direction divided by the length of a side of the box. Okay, so pressure starts as force. And Newton, Isaac Newton, defined force as force is created when a mass is accelerated, right? So force equals mass times acceleration. And acceleration is change in the value of the speed with change in time. So we can substitute this change in speed with change in time for the acceleration, and we get this. So the force of the gas, right, on the walls of the container is equal to the mass of one gas molecule times the speed of that gas molecule divided by the change in time. The change in speed with the change in time. Okay? And so, multiplying mass can move into the numerator, right? Mass moves into the numerator. And then, if we just move mass in, this mu here becomes, right? That becomes our momentum, right? So this numerator becomes the change in momentum with change in time. Okay? Change in momentum with change in time. Okay, so let's consider what our particle is doing, right? So our particle is moving in the x direction, right? We're only considering movement in the x direction, right? Across or back. And the collisions are perfectly elastic. So our molecule has speed u going in, it collides with the wall, and when it leaves, because it's a perfectly elastic collision, it has speed u going in the opposite direction. So if we take toward the wall as positive, away from the wall as negative, right? So now we can consider the change in momentum. So first the particle is going from going u to 0 when it hits the wall. So we have u down to 0. So that is a change of negative u. Then we have 0 up to negative u. That is also a change in negative u. So the change in speed is 2, right? So the delta of u is equal to 2 times negative u, right? Because we're slowing it down from u to 0 in the positive direction. Then when it goes back the other way, it's going in the negative, from 0 to negative u is another negative u change, right? So we've got mass times u, negative u going in, and we've got mass times negative u going out. There's our 2 times the mass times the negative u. So the change in momentum is negative 2 times the mass times the average speed, in this case specifically, right, in the x direction, right? We're only talking about movement at the moment in the x direction. But we could do the same kind of analysis in both the y and the z direction, right? So this could be done for all 3 vectors that we determined for the single speed vector. Okay, so we start off summarizing where we were on the previous slide, right? So our force of the gas is the change in momentum with change in time. We figured out that our change in momentum is negative 2 times the mass times the average speed. And so we can take that and substitute it there, which gives us this equation, right? So if the force on the gas molecule is negative 2 times the mass of the gas times the change in speed over the change in time, Well, then the force on the wall, right? Newton's third law of physics says for every action, there's an equal and opposite reaction. For every force, there is an equal and opposite force. If the wall exerts a negative force on the gas molecule, then the gas molecule exerts an equal and opposite force on the wall. So the force on the wall becomes positive 2 times the mass of the gas molecule times its speed in the x direction divided by the elapsed time, right? So now let's go back over here. Remember that the speed divided by the length was the collision frequency, and that it had units of 1 over time. Well, note we have a time unit in the denominator here, right? So if we can substitute the collision frequency for that 1 over time unit, we get this, right? So we're replacing our 1 over time unit here with the 1 over time unit we get from our collision frequency. And so we get then the collision frequency multiplied by this. Well, u times u is u squared. So now we get that the force that the wall is feeling is 2 times the mass times the velocity squared divided by the length of one side of the box, in this case, the x side of the box. Okay? Well, we've only been considering force in the x direction. We said we could also consider force in the y direction and force in the z direction. So if we take this expression with the velocity vectors in the x direction, this same expression with the velocity vector in the y direction, and then this same equation with the velocity vector in the z direction, and pull out what's common, 2m over L, we get that the force total in all directions is 2 times the mass of the particle divided by the length of one side of our cube times the velocity squared in the x direction, the velocity squared in the y direction, the velocity squared in the z direction, which we earlier defined as the average velocity, or the velocity squared. And so we've got a simpler expression of that relationship. Okay? So we're back to looking at the full vector as it goes diagonally across that box from corner to corner. Okay, so here's that equation. Our total force, 2 times the mass of a single molecule, divided by the length of one side of our cube, times the speed of our molecule in meters per second squared. Now, our definition of pressure is that pressure is the force divided by the area. And since now we're talking about molecules moving in all directions, since the area of one side of the box is length squared. And since a box has 6 sides and the gas molecules are going to hit all the sides, the area is equal to 6 times the length of one side squared. So the total area of the inside surface of the box is 6 times the length of one side squared, right? That's the area of one side. There are 6 sides in our cube. So now if we substitute that for the area, we get that our pressure is the force divided by 6 times the area of one side. Right? And if we take, right, force total we defined as this, so if we substitute this in for the force, we get this expression, which, right, 1 over length, we can move that down. So this length times this length squared gives us length cubed. And 2 over 6 is 1 over 3. So we get that the mass times the speed squared divided by 3 times the length cubed is our pressure. But length cubed is a volume, right? That's how we define our volume. So now we get that the pressure is the mass times the speed squared divided by 3 times the volume, right? So we're getting there a little at a time. Now remember, this pressure that we just defined is the pressure exerted by one gas molecule bouncing randomly, right, in all directions around our cubic container, right? One molecule. So now we need to figure out what the pressure is for a whole sample of molecules. So the number of the gas molecules are going to be equal to the number of moles times Avogadro's number, right? So if we want the pressure for the whole n moles of gas, we have to take the number of moles, right, times the number of molecules per mole times the mass of each molecule, right? Number of moles, molecules per mole, mass of each molecule, right? Where our average speed, now that we have more than one molecule, is the speed of each individual molecule, all summed up. And remember, we're using speed squared so that we don't have to worry about whether they're going in the positive or negative direction, divided by the total number of molecules. And actually, this would be n times Avogadro's number, right? So we've got an individual speed squared for every molecule in the sample divided by the total number of molecules to get the average speed squared, right? So that's what that bar means, is that we have taken the average speed, squared it, or we've taken the speed, squared it, determined the average for that. So you get the average squared speed throughout the sample. Because remember, some of the molecules are going faster, some are going slower. Okay? So this is represented by that. And so now we end up with this expression. If we bring our, right, if we divide both sides by the number of moles and we multiply both sides by the volume, we get PV over N equals this combination. The number of molecules times the mass of each molecule divided by 3 times the speed squared. But if we go back to what we said about the Boltzmann relationship, the speed squared equals 3 times Boltzmann's constant times the absolute temperature divided by the mass. So if we substitute that for the speed squared, we get this. But, right, 3 divided by 3 is 1. mass divided by mass is 1. Avogadro's number times K gives us the gas constant R. So all of this reduces to R times T. So we get PV over N equals RT. If we multiply both sides by N, right? If we multiply both sides by N here, and N here, N and N cancel, we get the ideal gas law, PV equals nRT, which is exactly what we determined experimentally by combining the individual gas laws. So it shows that what we figured out empirically, we can determine theoretically with a few basic assumptions.